So guys, I promise you that we are through the worst, not just the hardest stuff in chapter 17, but the hardest stuff in Chem 163. Section 17.3 is definitely the hardest stuff. And so everything from here on out is going to be significantly easier. The next section that we're going to cover, we're done talking about acids, acids and bases. Which I know you're saying, whoo, right now. So the next thing that we're going to talk about is solubility equilibria. So we're still talking about equilibrium, but we're not talking about acids and bases anymore. I'm going to draw a beaker. What we're going to be talking about in this section is the equilibrium that is associated with a solid substance dissolving and dissociating in solution. So let's say that we have a beaker with, we're going to put some water in this beaker. And we are going to drop into this beaker a chunk of silver chloride, AgCl. Silver chloride is an insoluble solid, meaning that it does not dissolve in water. Does not dissolve, which means it doesn't dissociate in water. And this was something that you learned in Chem 161. We had that solubility table when you were learning about precipitation reactions and net ionic equations and ionic equations and all that stuff. You learned how to look up different ionic compounds in the solubility table and determine whether or not they were soluble in water. And AgCl is one of those compounds that's not soluble in water, meaning that it doesn't dissolve in water and also that it doesn't dissociate into its cation and anion. So actually all that stuff that we taught you in 161 is a bit of a lie. These insoluble solids like AgCl, they actually do dissociate a little bit. So this is really not totally true. Now, if you're like, right now you're saying, oh my God, I can't believe you told me that they were insoluble and they did not dissolve when in fact they actually do dissolve. Don't be upset about it. They don't dissolve very much and they don't dissociate very much. It's a very, 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 very tiny amount. So AgCl solid, when we say that it is insoluble, this means that it barely dissolves or dissociates. Some of it does, but it does not dissolve or dissociate in water. The overwhelming majority of the silver chloride or any of our insoluble compounds, the majority of them are going to stay in the solid form, intact, not dissolved, not dissociating. Only a teeny tiny amount is actually going to dissolve or dissociate. And so for the majority of us, the majority of people, and the majority of chemists, we can just say, hey, it doesn't dissolve and it doesn't dissociate. And that's going to serve our purposes. It's a very small number of individuals who have to really think about the dissociation of these solid substances. So the dissociation of these insoluble solids is in equilibrium, which is why I drew these little equilibrium arrows right here showing that there is an equilibrium between the intact solid ionic compound and its cation and anion. And I know you guys know what that means, but let's just kind of refresh what exactly that means. So this is saying that there is a perfect amount and also a limit of how much silver ion and chloride ion can actually be dissolved, aqueous, in this solution. And so some silver chloride solid might dissolve and dissociate and form these ions, but if we get too much of these ions being formed, then we're going to see the ions coming back together and recreating the solid compound over here. So it's going to maintain this perfect balance of the concentrations of the ions in the solution. We can write an equilibrium expression for this reaction, and we're going to leave a little space right here because I'm going to give it a subscript, just like a Ka or a Kb. Remember, the equilibrium expression is products over reactants raised to their stoichiometric coefficients. So we have Ag plus and Cl minus, our products, and they both have a coefficient of 1. And then that is over the reactants, but we leave out solids and we leave out liquids. And since our reactant is a solid, we have nothing to put down here at the bottom of this fraction. So there just isn't anything there. It's not a fraction. This K is not a Ka and it's not a Kb because it's not an acid or a base. We call this a KSP, and the SP stands for solubility product, and the KSP is the solubility constant, because it's talking about solubility. So right now, all that I want you to do, because you've done so much with section 17.3 already, all that I want you to do right now is just write these equilibrium expressions, these KSP expressions, and that's it. We're not going to do anything more hardcore than that yet. We'll save that for later. So let's look at another reaction. MgOH2 magnesium hydroxide. This is another quote-unquote insoluble solid, meaning that only a teeny tiny amount of the cations and anions are actually going to dissociate. Now this one is a little bit more interesting because we have 2 hydroxides in the magnesium hydroxide compound. That means that we're going to have 2 hydroxide products when this undergoes dissociation. And so when we write the equilibrium expression, the KSP for this particular compound, we're going to have, for the first time in a long time, we're going to have a stoichiometric coefficient to deal with. With our acids and bases, everything has just had that coefficient of 1 for so long. We haven't practiced this in a while. So remember, because we have 2 hydroxides, that means that we're going to be raising the hydroxide concentration to it too. Let's do one more. The next one we're going to do is silver sulfide, AgS, in equilibrium with 2 Ag plus aqueous and S2 minus aqueous. And let's write a KSP for this one. Products over reactants raised to their stoichiometric coefficients, leaving out the pure solids and the liquids. Paying attention to stoichiometry, we have 2 silver ions. That means that we have 2 silver cations. That means that we have this superscript of 2 in the KSP. So the last thing that I'm going to talk about is just going to be stuff that was reviewing when we were first talking about equilibrium in 162. The magnitude of the numerical value of KSP, or just equilibrium constants in general, Ka versus Kb, KSP, KEQ, Kc, whatever you want to call it. The size of the value of the equilibrium constant tells us a lot about the extent to which it reacts. So if we have a compound that has a really big value of KSP, if KSP, let's just look at the one up above it, if KSP is really large, that means that these concentrations are high. Those are going to be big numbers in order to produce a big KSP value. So if we have a big KSP value, This, another way that we would say this is that the position of equilibrium is to the right. Our substance is more soluble. It has a big concentration of products. And this is the same as what we talked about in 162 when we were looking at the values of K. If we have a small KSP, a small equilibrium constant, our position of equilibrium is to the left, which means that we have a small concentration of our products. And that means that our substance is less soluble. It does not really want to dissolve very much. I feel like I want to explain that again. I'm going to do one more. So FeOH3, we're going to get real exciting here. In equilibrium with Fe3 plus aqueous and 3 OH minus aqueous. And let's write an equilibrium expression for that. KSP equals Fe3 plus and OH minus cubed. So I'm going to say all this stuff right here, but using maybe different words that are going to make more sense. So if FeOH3, if it is a very soluble substance, if it's very soluble, that means that its position of equilibrium lies to the right. If it's soluble, it's dissolving and it's dissociating and it's producing large concentrations, large amounts of the cation and the anion. So in the KSP, those concentrations are going to be large numbers, which is going to result in having a big KSP. If the KSP is a big number, the solid is very dissolved and also very dissociated. On the other hand, if the FeOH3 is not very soluble and it's not dissociating and the position of equilibrium is over here, we have very small concentrations of these products. The concentrations of iron ion and hydroxide ion are going to be very low, which is going to result in giving us a small value of KSP. If the KSP is small, the solid is barely dissolved or dissociated. So the value of the KSP gives us information about how soluble, how much a solid substance is willing to dissolve and dissociate. We can also use the value of KSP to make predictions about the saturation of a solution. So let's do another example, PbF2 solid in equilibrium with Pb2 plus aqueous and 2F minus aqueous. For this particular reaction, and for all of these solubility reactions, when we are in equilibrium, we will say KSP is equal to Pb2 plus for this guy and F minus squared, so we're in equilibrium. And the solution, we will also say the solution is saturated. Remember, saturated means maximum amount of our solute, our solid, the maximum amount of PbF2 has dissolved. So when we are in equilibrium and we've got the maximum amount of this reaction taking place and we have the maximum amount of our products, we are in a saturated situation. So when we're in equilibrium, we are also saturated. And the KSP is equal to the concentration of the lead 2+ ion and the fluoride ion squared. If we're not in equilibrium, so if you remember back to 162, that means that we can't say KSP anymore when we're not in equilibrium. We use the letter Q instead to indicate that we're not in equilibrium, or we're not sure if we're in equilibrium or not. We calculate Q the exact same way that we would calculate K, and then we compare Q to K. So if Q is less than KSP, that means that these concentrations are smaller than they need to be, or smaller than they are supposed to be. This tells us that the solution is unsaturated. Unsaturated. Unsaturated meaning that we have less than the maximum amount of PbF2 dissolved. We have not enough product. And the position of equilibrium is going to need to shift to the right to help it dissolve. If Q is greater than KSP, this is where we have a supersaturated solution. The solution is supersaturated. Supersaturated, we've talked about before, that means that we have more than the maximum amount dissolved. So we've done something to trick this solution into having too high of a concentration of our ions. So there is too much product in this case. It's unstable, and so it needs to shift its position of equilibrium to the left to get rid of some of that extra product. And then, of course, if Q is equal to KSP, that means that we are perfect and the solution is saturated.